Welcome back, everybody. Welcome back to the channel. So, have any of you guys ever wondered how Java's JNI actually works, or how to build a JNI or a native interface to bridge your programming language into C++ and more? Those are going to be the topics of today's video, so let's get right into it. So, what we're going to do is I've already gone over the high-level portion of actually how to parse native into your programming language. So we're just going to jump right into it and we're going to look at every aspect of the system in order to see how it works. Now, first, we're going to have a native function. So we're going to say native define foo, and foo is going to, let's do something very simple. So we're going to print hello world. So we're going to say load underscore library. I'm going to load library of, I don't know, foo, and then we can call the foo function. And what's going to happen is we're going to dynamically load this function. Now, I'm not going to go through 100% of the entire cycle to actually show you guys this because it's pretty straightforward in how the system actually works. It's actually a lot simpler than you think. Not to mention, I don't want to make this video too long by writing too much crap. So let's just kind of do the C++ side of it to kind of move things along. So we're going to say foo.cpp, and what you're going to want to do is we're going to want to include, so I should do hashtag include, and you want to include what's called native mapping. Native mapping.h is going to be a source file that's going to be generated by our compiler. Now, I'm not going to get into the specifics of how this source code is generated because we're going to focus on that on the compiler side. Right now, I want us to focus on mostly the virtual machine and runtime engine side first. So before we get into the native mapping.h file, which is in a generated folder, you can also specify where you want this to be. So actually, let's do that first. So if we go to the runtime, or actually no, it's in the compiler. So if I go to grammar, I go to main. If we do a search for an option called nd, it's going to be a -nd. We're going to basically have a new option now in our compiler called native dir or -nd, and specify the directory where we want to basically put the source code. Now, by default, what our compiler is going to do is it's going to create, or if the folder is already created, it's going to dump a bunch of files inside of here that we can then use to actually run our programming language. So, as you can see, this allows us to set the output code directory. And basically, so if I do a search for ND, we're going to have both of these options here, and it's fairly simple. We need to have an additional argument afterwards, so obviously we want to protect against that. If we do not have an additional argument to read, we will say output file required after option. No, that's actually wrong. I think this is, yeah, this is a copy paste error. You want to say output directory, directory. So you want to say output directory required after option whatever, and it's going to be based on whatever was passed in here dynamically. If we have the option, then we're going to have to create a new field called native directory. And as you can see, the default folder is going to be generated. So the compiler is effectively going to create the generated folder in whatever the current working directory that you're compiling the source code in. So keep that in mind as you're, coding it and everything. But we'll see more of that later. So once we kind of have that generated file, we basically do dynamic loading of functions. Now we'll get into the system of how dynamic loading works in a second. So once you do that, let's go back to the CPP file, the foo.cpp. So after you include native mapping, you want to create what's called a scope. And it's going to be scope begin, and you want to begin a scope based on where we are in the source code. So currently we're in the module of app, so you want to create a scope of app. And once you do that, of course, you say scope scope underscore end, and you want to actually end the scope. Now, inside of here is where you actually put the source code for defining your C++ functions. Now, my programming language, unlike other languages, specifically more so on the Java side, it's a huge pain in the ass to do all of this. Now, I've already kind of gone over 2 demos of this, but just for the purpose of this video, I'm going to go over everything once more. So, we want to create a foo function that is replicated in the C++ level. So we want to create a void because it doesn't return anything, foo, and that's it. And then we can just simply say cout, and then hello world, comma, world, and that's literally it. And we will, if I actually were to go through the entire process of compiling this by the compiler, taking these source files, loading them into a DLL, and then running that DLL alongside of the source code, we would get hello world after we ran the program. Again, we're not going to go through the entire process because the video is going to be too long. So now let's actually see how this code works. So I know I've said before that we have a concept called dynamic loading, but you can also do static loading, or you can force a load on a specific function. So there's actually a function called, and it's actually located in the, is it in platform DL? I don't actually remember. So if I go to the support 0.2 platform DL, yeah. Okay, so it's in the platform class. So there's a function called load underscore function, and we'll go over this as well. So, or no, it's actually called link, which makes more sense. So you can link a function to a very specific DLL, and this is very helpful if you may have the same function defined with the exact same flags and the exact same name inside of a different DLL, and you don't want to have issues where it links the incorrect function. So what you do is you pass in the name of the function and then the library that you want to load it. So in this case, we would want to load the foo function from the foo library. And that's going to then link this function at the low level to the function that's defined inside of the DLL or SO file that's going to be defined here. So now let's look at how all of this stuff works. So first we're going to go down, as usual, we're going to go down level by level to see how everything works. So we're going to start up here, and I'm actually going to leave this code in. So I'm going to start and look at the load library and link functions. Now this feature that we're going over today is going to require cooperation by all sides. So typically when I show you guys a feature, it's typically more heavy on one side than the other. It's mostly like the compiler tells the virtual machine to do a few things, and the virtual machine just takes care of everything. Or in different instances, the compiler does most of the work and the virtual machine just says, okay, I'll do whatever you tell me. However, in this case, this is going to be a very complex feature, so we're going to need both the runtime system and the compiler to cooperate on both ends. So when we load the library, we're going to be calling the platform functions that are going to be defined in our platform class. That's going to be in the kernel section of my standard library, and we're going to have three standardized functions: the ability to load a library, the ability to free a library, and the ability to statically link a function directly to a DLL. So if we go down one more level, this is the platform class. Now, this is where we start at the very beginning of executing code in Sharp. So, as you guys know, you've seen this function before, SRT init. This is the main starting point of every Sharp programming language. So what you want to do is you want to create a bunch of different functions. So obviously we're going to create the load library, free library, and link function. And what we're going to do is, depending on which one, pass in different parameters. So when it comes to loading a library, we want to get the library's name and we want to get the library path. Now, this is where it gets into operating specific instances. So when it comes to actually programming your programming language to work on both Linux and Windows, obviously Windows has a .dll structure for dynamic libraries and .so for Linux-based libraries. Now, typically a good rule of thumb is when you're actually, for instance, when you're just saying foo, you don't want to have to force the user to say whether or not it's a .so or a .dll. You want the system to try to dynamically figure it out based on what operating system we're currently operating on. So you want all that work to be obfuscated. You also don't want the user to have to worry about where exactly is this actual DLL stored. So obviously, this is assuming that the DLL is stored in the current directory of the function. However, if you do not specify the full name, you will run into errors. This is mostly for Linux, where you'll have to, for .so files, set up where you're actually going to be pointing to that actual DLL in your system files. It's kind of a mess, so it's better to just provide the full path to the actual file, so that way you don't have to worry about any headaches with either operating system in actually finding the DLL. So if we go back That's what this Git library path is going to do. It's going to find the actual library based on, obviously DLL or SO, and then it's going to return the full path of that library. So we're going to put that on the stack and then call the respective system interrupt depending on what we need to do. We do the same thing for free library, and this time we return a result. So we're just going to return that result back to the user. We're also going to link a function or attempt to link a function, and we can also return the result back to the user. And as you can see, we are in fact pushing both of these values onto the stack. Now I push both int arrays or string arrays to make things easier. So that way I don't have to worry about accessing fields inside of classes, so I can just get the actual names off the stack. So I call get data, which is in the string class, which literally just returns get score data, the actual data. And if I do a search for that, well, that's going to be all over the place. But if you scroll back to the top, it's actually returning an int8 array. So you want to return an int8 array for both because it makes things easier. So now let's actually look at the get library path function. It's a very simple function. Literally, we end up checking to see if build is Windows. And what that's going to do is then go to the build file, and it's going to check to see if the OS is equal to Win or if the OS is equal to POSIX. And depending on which one will depend on what we do. So if I go back to the platform class, you can see that if it's Windows, it's .dll. Otherwise, I append .so to the end of the name of the DLL. Then what we're going to do is we're going to use my file system API written in my programming language to basically create a new file, pass it the name, and then get the absolute path on that file, and then get the actual data. And get data is actually it's calling the get data from the string class that we just went over. I don't know where it is, but if you guys remember, we just recently talked about it, where we're actually pulling out the actual contents of that. So if I go to, where is it at? It's in file.sharp, and I say get underscore absolute path, you can see that it returns a string. So that's what we're actually doing. We're not getting the actual content of the actual DLL. So I wanted to be very clear about that. So what that's going to do is return us the full path in a int8 array string format, and then we can take that and pass it in. Now, here's where the magic happens. So now let's go down to the next level, which is the runtime system level. So if we go down to the runtime, if I go to the virtual machine, it's actually at the very end. Okay, so there's a couple different opcodes. So I'm actually going to set the compiler to, or set the virtual machine to be compiled, and that way we can get proper syntax highlighting. But as you can see, I've created three system interrupts for the actual system that we're going to be using for the JNI. And we have a load library op, a free library op, and a link function op, just like the three functions we just saw. So for loading a library, here's how I do it. Basically, when it comes to loading a library, I get the lib name off the stack. And remember, this is going to be an int8 array. So we're going to be expecting a underscore int8 array from the actual stack. And then I do some checks here. So I check to see if the lib name object is not equal to null, and in fact, it's a var type or a numeric type. And I make sure that the head is not equal to null, which is just the numeric array value of that actual object. So now that we're absolutely sure that we have information, we get the name by passing it into the native string class, and I pass it the size of the object. Literally, all that's going to do is pass it the double value and the max value, and it's going to set that value onto this native string object. And it's literally just going to create a char array based on the size that we passed in here and just assign those values from a double pointer. So if I go back here, and then after that, we guard the threads monitor. This is going to be a static mutex that we're going to be using to basically guard the entry point of this code here, because we don't want multiple threads trying to load a single library. So we want them to run one at a time. So when we get down to here, we're going to check to see if we can actually get the library from our system. So I'm going to pass in the name of the library, and we're just going to go through our list of libs. Now, what this is going to prompt us to do is in the virtual machine, create a list of a library, which is going to represent our DLLs. So in this class, it's pretty simple. Basically, I just have a basic class with an init function and a basic constructor. And in there, I have the actual name of the DLL or SO file. And then for Windows, it is H instance. For Linux, it is void pointer for the handle of the actual library. So it's a pretty simple class. So once we've verified that we can actually get the library, if we actually find the library, that means that, there's no point in loading it because we already have it, which is totally fine. So if the library is null, we go into here. Otherwise, if the library is not null, then we just free up the name, which, frees up this data structure that we created, and that's it. We just return out of here because nothing needs to happen. Now, obviously, if the lib name object that we passed in is null, we're going to throw a null pointer exception because that's obviously an issue. Now, when we get into this actual code, we're going to create a library field here, and then we're going to do things based on which operating system. So if we're not in Windows, basically if we're POSIX, what we're going to do is create a character called liberr. And the reason why you want to do this is you need this variable to ensure that everything is okay. So this is based on the man file or the man page that I got from Linux, where they basically recommend you to call dlls to basically ensure that you have absolutely no errors after you try to load the library. Otherwise, if you do, then you can print out the error. So I'm going to say the handle of the library, which is dependent on the operating system, is equal to load lib, and I pass in the string of the actual name that we need to load. Now, this load lib is a defined statement that is dynamic depending on the operating system. And for Windows, I call load library, and that is found inside. I'm going to be honest, I have no idea where that code is, but I'm pretty sure it'd be very easy for you guys to find out where this load library stuff is being called. It's actually inside of winbase.h. So however that is inherited, for those of you who are curious, that's the actual file that you need to actually call this function. And for Linux, we do the same thing where we load the library, but instead we call dl open. And what I do is I say dl open, I pass in the library's name, and you want to pass it the C string, which is the constant char version, and I say rtld lazy. What that does is that lazily loads the library based on the components that we need to require access to at the time of loading the library. That way, this allows us to have as little errors as possible when it comes to actually loading the library because it doesn't require us to have all of the components immediately. So that's kind of what I do. And then if we go back, I assign liberr equal to dl errors. So I'm basically getting the error if something happened here. Now, if the lib handle is equal to null or the lib error is not equal to null, meaning that there was an error while loading the library, then we're going to free up the name. And if it's Windows, do I do something? Oh yeah, I do something different. So if it's Windows, then what I do is I throw an exception and say illegal state exception could not load library, and then I pass in the name of the library, which actually that's bad. So I'm going to create a string lib name is equal to name dot string, and then I'm going to call name dot free, and I'm going to say plus lib name. That way we can actually have access to that because you want to protect against memory leaks. Like we're allocating this object and you want to make sure you free it because yeah. So that's what we do, and that's pretty much how I handle it. Now for Linux, what I do is I say illegal state exception, could not load library, and then I print out whatever the lib error was for Linux. So I'm actually going to get a detailed error as to why the actual library could not be loaded from Linux, which is really nice. For Windows, it just says, oops, it failed. So for that, now we start getting into the theory behind how my actual system works. So I have the concept of what I call a handshake. All a handshake does is it is a basic way for me to ensure that this is in fact a authentic sharp API that we can interface with. So the lib handshake is just a function where we pass it a void pointer of lib functions, and then I pass in an integer of the amount or the size of this array, and it returns a short, which basically represents whether or not the handshake was successful. And this allows us to basically protect against if I have potentially different versions of my JNI, then I can protect against that as well. So if I go, where is it at? So I have a SNB folder here, and the way it works is it's a contract between code that I've personally written and the user's code. So it's a bit of an interesting system. Basically, the API has a function in there where's it called? It is the SMB handshake. So if I go to the SMB API, we can see there that we have the exact same signature, which is handshake, and that's in fact what we're looking for. So we're looking for the SMB handshake. So that's going to be defined. Where is it at? So if I go back here, that's going to be defined all the way at the very bottom. So this is going to be an exported function, and I have this code here where I basically defined a way to have cross-platform imports and exports. Now in my case, I'm only using exports because that's all I care about. So this is how I do it. So if it's Windows or Cygwin, I say exported attribute DL export. I say not exported, just does nothing. Otherwise, if GNOC is greater than or equal to 4, I do this stuff. Otherwise, I say exported, not exported, and nothing happens. And yeah, we never should get down to this portion in the code. We should typically stay up here because it works for both Linux and Windows. So this is a very easy cross-platform way for you to create exports for your programming language when you actually export a DLL file. So what you want to do is create a check to see if not defined or if defined C++. Then you want to say extern C whatever, and you want to export the actual source code. And again, we're going to have the SMB function, which is the SMB handshake. Then we call the SMB API internal handshake, which is defined up here. And all I want to do is check to see if the amount of functions that we need to process are in fact equal to the functions that we have in here. Now, of course, you can do more. Like, I'm still in the process of building this system, but you can pass in an int of version, to clarify that you are in fact running on the exact same version of the JNI that your programming language is going to have. I mean, you could do all sorts of stuff, and you can pass in different types of data. Now, one thing I will say before we continue on, and I'm going to mention this again, I think later on in the video. However, when it comes to passing information across a DLL or an SO file, you do not want to pass across objects. You want to pass across simple data sets. And what a simple data set, what I mean is you want to pass across objects that are always going to be a fixed size because it's that size always on the operating system. Now, I know that seems a bit weird. Basically, what I mean is the way that C++ works is if you create a class, right? Let's call it foo. And let's say, this class is an int called x, and then we have, I don't know, an int of size or whatever. And we may have, more fields down below. Well, whenever I, have a function, so if I say void foo, and I have a foo function where I say, actually, foo, let's do that, function. So I have this foo function, and I create a foo f, and I say f dot x is equal to 100. There's a problem when it comes to doing this, because basically the way that our source code and our compiler is building out the structure layout of this actual object may be different than the user that is actually passing data and compiling it with their function. So what I mean is we may be using a version of the GCC compiler where it creates the object of foo and it pads it to a total of, I don't know, let's say the foo function was 32 bytes, right? And let's say the actual class had, its field of x, and then, that took maybe 4 bytes, and then let's say it had 0, or let's say it had like 2 bytes of padding or something like that. And then we had an additional field of size, which, I don't know, let's say again that's another 4 bytes. And then let's say it had maybe 1 byte of padding or something, right? You guys get the point. So, and if we had obviously more fields after that, then it would, have its own format. But then let's say the user wants to come around and they want to interface C++ with our programming language. Well, let's say they're using a super old ass version of GNU or the GCC compiler because they, I don't know, maybe they just didn't update their system or whatever, it doesn't matter. They're using a different version of the compiler. Now, instead of, having this, maybe the foo class still is, 32 bytes wide because maybe that's just the size that it ends up being because of the simple objects that it has in there. But then let's say instead of having 2 bytes, it has 1 byte of padding. and then this one has 2 bytes of padding. Now the physical ones and zeros that make up the first object, and I know I'm getting like super low level, guys, please bear with me, I'm trying my hardest to explain this, is now different than the ones and zeros inside of the second object. But in essence, they're trying to represent the same class. They're both trying to represent the foo class, but the problem is that each compiler has their own way of doing the bit layouts and formats of their actual classes at the low level. I hope that made sense. But yeah, so you just want to be very careful. And a rule of thumb for me, in my opinion, is just use void pointers. Do not pass any hard objects, and we'll see that shortly. So, and this is probably going to be a part 1 because this video is going to be a long ass video, and I just don't want to do another like 1 to 2 hour video. So I'm going to do a part 1 of this, and then we'll just, continue from there. So let's just go all the way up until the point to where we can actually load a library. So what we're going to do is, for me, I'm checking to see if the size is equal to the size of 26, which is how many total internal functions that I have. Now I have this data structure or the structured way of coding, where I have a namespace called the SNB API, which represents the API that we're going to be interfacing with as the user to do all the various things that we need to do. Like, let's say if I go back to the syntax function, and let's say I have an X now that's supposed to be a var. Well, this is going to force me now to say a var of X, right? And this is going to represent the actual variable that we just created as a parameter that we're going to need to pass in. But there's a problem. We now need to import, or say using namespace SNB underscore API. And this allows us to utilize the SNB API, which this var class is a part of. So that's kind of the format. So I'm going to go back, and I hope you guys are still staying with me. I know this is like a lot of information. So then we want to basically set up all of our functions by assigning them and casting them to basically the format that we need. Now, at the low level, guys, I mean, C++ doesn't give a shit like what any of this stuff is. It just sees an array of void pointers, and we can cast it to whatever the heck we want. So again, you want to be very careful with this, but basically I'm casting all these functions to functions that are actually located inside of the actual platform. So these are going to be functions that I'm going to create inside of the actual virtual machine, and we're going to be passing that data back. So if you guys imagine, let's say we have, I don't know, we have the executable, and the executable wants to communicate with the actual, let me put a V here, the executable wants to communicate with the DLL file. But there's a problem. So first we need to call the handshake. So first we need to say, if I put a dash here, whoops, and then I put another pipe here. Then if I do this, you guys get the point, and then handshake. So we want to basically handshake with the actual, from the exe down to the DLL. That then allows the DLL to say, hey, executable, I have a function that I need you to call. So the DLL is going to then go all the way backwards to the actual function to actually call, whatever it needs to call. So if I put an arrow here, just a bunch of dashes, this allows the DLL to, go back up. So that way it's a full circle. So the exe can then call into the DLL and call the foo function that we talked about in the syntax file here. And then if we go back, then the DLL can then subsequently call data into the exe to, again, protect against that weird ass memory mapping that we may potentially have in our programming language. So again, all these functions are going to be on the actual virtual machine. And then what we're going to want to do is just return whether or not all of these have values. So we're going to say increment reference, decrement reference, frame pointer number add, getting the field, getting the var pointer, and so on. So all of the internal functions that we're going to need to call back into the virtual machine are going to be required to have an actual address. So once we do that, otherwise, if that's not true, then we just return false if the size of the functions is not what we expect. Also, we are going to have a bunch of other functions that we'll get into a little later. So let's go back to the virtual machine. So once we've successfully handshaked, then we basically say lib handshake. So we do a check to see if we actually have the address of that function inside of this DLL that we're trying to load, and we say setup library. So what setup library is going to do is we're going to pass it the lib handshake function, which is, this function here that I just explained. And if I remove this code, we're now going to just pass it the array of void pointer to the lib functions that are referencing all of these functions inside of our virtual machine that are going to interface with the virtual machine to do everything that we need to do. So the way that my programming language is going to work is everything is going to be managed by the virtual machine. So if I go back to my example, so once we do a handshake, we're going to call the foo function, right? And we're going to call that into the executable. The DLL is then, let's say at the low level, instead of this being a var, we're going to create an object, right? Object, and this is going to be an object of, I don't know, a foo class, right? And we have our foo, and then we're going to say foo underscore function, whoops, foo underscore function, and then we're going to need to update this name, so foo underscore function, and we're going to then subsequently create a class called foo. So we're going to create a class of foo, and this foo is going to have a x of var, and that's it, right? So now let's say at the low level we want to actually access this foo class. I'm not going to get into the specifics of how this works yet. This will be in part 2, but we're going to create a var of the x field, and I'm going to assign that equal to, and what is it? Get underscore field, F-I-E-L-D, I don't even remember. Var, we'll go over the specific function later. So we're going to say get field of var, and we're going to pass it the foo object, and then we're going to say the x field. That's going to give us a var of x, and then we can just say x is equal to 100 or whatever to actually access that. The way that this is going to now work is we're going to now have to call back up to the actual virtual machine and say virtual machine or executable, please provide me with the object of, foo. The executable then talks back to the DLL and says, okay, here's the object, and then the DLL then does whatever it needs to do. And then once the DLL is finished setting up this field, and then we subsequently say x is equal to 100, the DLL is going to then bug the executable again and say, hey, executable, I need you to actually set the field of x that you just gave me to the value of 100. The executable then says okay, and then that's the end of the transaction. So that is kind of how it works. The DLL really isn't doing much work. We're mostly requesting stuff for the executable to do. That's why I have this SMB API function with all of these things to like increment references of objects, decrement references, getting the pointer of a variable, doing stack stuff, calling functions, pushing stuff onto the stack, just everything, right? I even have some exception stuff in here. So recently, I've just actually added support for my exception system into the actual JNI. So that's going to be really interesting. The entire concept of how this is going to expect it to work is we want this to be as high level as possible. Now, I'm not going to get too much into detail, but let's say, we wanted to call a function at the high level. So let's say we had a function called, I don't know, work, and we wanted to actually call this at the high level. We would then subsequently, create a function here, define work, and let's say work throws an exception, so it throws an error of, whatever, right? Eventually, at some point, we do some code, right? So we do some code before, and then it throws the error of whatever. Then we can literally just do this, right? I don't know why programming languages make this so difficult. We can just try, and we can then catch CATCH. We can catch that exception, EXCPTION of E, and then we can do some stuff with that exception. So we'll go over this later on about how that works. And this is kind of nice because we've already talked about our exception system already. But again, the concept that I'm trying to bring to you guys is I want coding in C++ to be as close to the goddamn language as possible, because it shouldn't be this hard. Like, it should be very easy to just program in the language and interface with C++ in my own language. So we're going to go over all of that tomorrow. So this is going to be the end of part 1. So I hope you guys enjoyed the video. As usual, if you have any questions, definitely put them in the comment section below. And as always, if you guys would love to help support the channel, you can always head over to the GitHub repository at entrodevcd/sharp. And when you do, definitely watch, star, and fork this repository. That gives this language a ton of more visibility and let other developers know this language exists. Also, if you guys are curious about some of the stuff that I've been up to recently or some stuff that I'm looking to add in the future, you can always head over to this section right here. This is the roadmap section. This is a live view of everything that's going on with the programming language, so it's a really nice way to see what's going on in real time. So that's going to be it for today, guys. As usual, if you're new to the channel, definitely consider subscribing, and until next time, see you guys later.